Okay, let's start. And good evening, everyone. Welcome to the lecture 6 of BSE 534. I'm Dr. Huang. I'm a research assistant professor in Department of BEEE. And you can also call me Yunke, or you can call me Dr. Huang. And today we will have discussion on the application of the fire safety engineering to the fire safety design and management. Okay, let's share the screen. Okay, so this lecture builds on some previous sessions, and we will introduce both the prescriptive and the performance-based approach to the fire safety. And here is the overview of what we will cover today. So we will start with an introduction to the two main approaches in the fire safety design, that is the prescriptive approach and the performance-based approach. Or we can also call it fire engineering-based approach. Then we will look at some key references, including the local and the international standards. And after that, we will discuss some active fire safety provisions, like the sprinklers and the detectors. And finally, we will go through some practical examples using our fire simulation software. Okay, so in Hong Kong and indeed in much of the world, the approach to fire safety for the building design generally follows one of these two distinct philosophies. That is, as I mentioned before, the prescriptive approach and the fire engineering approach. So, firstly, we have the prescriptive approach. Think of this as a traditional rules-based method. Here, our designer or the engineering functions somehow work like the chef following a very detailed recipe. So the recipe in this case is a set of code of practice, code notes, and circular letters that are issued by the authorities. So these documents will provide extremely specific and step-by-step introductions for our designer. And they will tell you, for example, how many exactly staircases you need for a building of a given height and the area, and the precise minimum width of those staircases and the corridors, and also the maximum distance that any people should have to travel to reach an exit. So the great advantage of this approach is its clarity and the certainty. So if you follow all the rules exactly, your design is deemed to satisfy the ego requirement. So it will provide a clear checklist for both the designer and the approving authorities, making our approve process relatively straightforward for the conventional buildings. So for most of the standard residential, office, and the commercial buildings that we have in Hong Kong, there is still the predominant method used for designing escape routes. So what are these prescriptive codes? In Hong Kong, they are often referred to as 1+2+3 code. So the 1 refers to the general building requirements from the BD. So what does BD mean? Anybody knows what does BD mean? That is the building department. And the 2 is the means of the escape, that is MOE code, and the means of access, that is MOA code for the firefighting. And the 3 is the fire resisting construction code. And additionally, there are the FSI code. So what does FSI mean? That is fire service installation. So the FSI code is for installed system. However, those code may not cover every unique building design, which is why we need FEA. So FEA, as known as the fire engineering approach. Let's briefly look at the this second approach. So this is a fundamentally different way of thinking. It moves away from simply following a set of rules, and instead of we focus on demonstrating performance. So the designer will ask, instead of does my design meet every single clause in the code, the fire engineer will ask if in the event of the fire, will everyone be able to evacuate safely, and will the building structure remain stable? So this approach will use a kind of scientific and engineering principles to analyze and approve that the design will reach these safety objectives. So this kind of engineering principles, including the physics, the chemistry, and the human behavior, psychology, and even some advanced computational models. So it is not about ignoring the codes, but it is about understanding the intent behind the codes and finding some alternative, often more innovative way to meet the requirement of our fire safety. So this flowchart, it is from a research by Professor Cho. It illustrates the approval process. So it shows the 2 parallel streams. So one of it is the prescriptive-based code design, that is PBC, submitted to the building departments. And the other one is the fire service installation. So this FSI is submitted to the fire service department. So the key takeaway is that the decision point, that is shown here, FEA, fire engineering approach. So if the design code does not comply with the prescriptive code, the designer can propose an alternative solution using these FEA principles, which is a performance-based methodology to demonstrate an equivalent level of safety. So imagine you are designing an office building with a huge, beautiful atrium. So the prescriptive codes say that you need to fill this atrium with fire shutters, which would destroy your whole beautiful design. So you can take the FEA passes. You don't just submit the standard plans. Instead, a fire consultant can create a report using the computational simulation. So this report will provide with a powerful smoke extraction system that the atrium is actually safer than if you use the shutter. So you submit this FEA report to the building department and the fire service department. So they review the engineering analysis, and if they are convinced your innovative design will get the green light. So that is why we need FEA pass. It is a crucial gateway to allow some modern and innovative architectures to be built safely. So in case of fire, the escape routes is one of the most important concern for designer. So for these escape examples, let's briefly look at the prevention of means of escape. So what does the prescriptive code cover for this kind of provisions? For means of escape, they provide the fixed figure for designer, such as the occupant densities based on the building type, and the number of staircases required, and the discharge rate, and the maximum traveling distance, or the minimum staircase width. So these are based on the historical data and the conservation assumptions. Similarly, for the construction, the codes prescriptive the use of the non-combustible material and assign specific fire resistance period, such as 2 hours, to different structural elements like walls, doors, and the floors. So the goal is to ensure the integrity and the stability to protect both the structure and the occupant. So as we talked before, the prescriptive approach has several critical limitations. So the designer will follow the code without questioning the actual performance. So we highlight the actual performance because it does not model how a fire would actually develop, how the smoke would spread, and how people would truly behave in the emergency in that specific building. So it just assumes that compliance equals to safety. That is not great. So for the complex building, this assumption can be tested, which is why we need a more analytical method. So therefore, for buildings with some special features, such as the large atrium, underground space, and the innovative architectures, the prescriptive approach may not be sufficient for even impossible to apply. So in these cases, the fire engineering approach or performance-based design become not just an option but a necessity. So this approach does not use standard figures. Instead, it applies scientific principles to prove safety, as we mentioned before. So this is a perfect example. You know what this building? Anybody knows what that building means? So it is the HSBC building in the central. So its beautiful design features a massive open plan atrium. So this is a very special feature that makes compliance with the prescriptive code impossible because they would require physical fire shuttle that destroy the architecture concept. And instead, a performance-based fire engineering approach was used for this building. Engineers can design a powerful smoke extraction system to keep the atrium tenable, analytically proving that this solution provides a level of safety that equivalent to the prescriptive requirements, and allowing the innovative design to be realized safely. Okay, so after our brief introduction for both prescriptive code and the performance-based code, now that we understand the why, and let's look at how. So we rely on several key references, starting with our own Hong Kong Code of Practice 2011. So this code of practice, updated in 2011, is a very significant document. It formally integrates the fire engineering approach into Hong Kong's regularity framework. So it provides a guidance for both traditional and performance-based design, making it an important reference for any fire safety engineer working here. So this is part G of the code. And the part G of this code is dedicated to fire engineering. It provides a local framework covering everything from the basic methodologies and the fire safety subsystems to the required content of the fire safety assessment report. So it is your first point of reference for any FEA project in Hong Kong. And before 2011, And in 1998, Hong Kong Building Department published this PNAP 204. The PNAP 204 is the framework of the performance-based fire engineering approach. It works as an alternative to the traditional prescriptive fire safety design. And after that, the Comprehensive Code of Practice for Fire Safety in Buildings 2011 now served as the primary resource and replacing this PNAP and offering detailed guidelines for the fire safety design, including the performance-based approach. But you can also take a look at this flowchart. So this flowchart is from the PNAP 204, still summarize the fire engineering approach process. We firstly identify the non-compliance and propose the alternatives. We then define the fire scenarios, understand the occupant behavior, and carry out a fire engineering analysis. So it is a cycle of analysis and the evolution. So beyond Hong Kong, we have some international standard. So the Society of the Fire Production Engineering Guides is a solid document for performance-based design worldwide. So its second edition gives an extensive guidance on the entire process. So look at this figure. Look at this figure, we can understand it is a kind of iterative process from define the specific measurable objectives and the performance criteria and to evaluation and the modification of the design. Now let's introduce the very extremely influential document, and I think it will show in your final test. So that is the British standard, BS 7974. So you can pay your attention on this part. So it provides a comprehensive code of practice for applying fire safety engineering principle, showing a global evolution of this idea. BS 7974 is supported by a series of published documents, as known as PD. So each PD covers a specific subsistence of fire safety. And the published document 00, part 00 is the guide to the overall framework, while part 1 to part 7 focus on specific area like fire development, smoke spread, structural response, and the detection and the fire service intervention, and finally the risk assessment. So this modular approach is very powerful for our fire design. So for BS 7974, the process involves the two key steps. So please take your attention on this part. The first one is quantitative design review, and the second one is quantitative analysis. So the quantitative design review, which is a systematic team-based review for the design, and the quantitative analysis, we use the engineering calculations and the models to analyze the design against the criteria. So the result must be satisfactory before proceeding. Here is the critical step for undertaking the QDR. So let's firstly look at the quantitative design review, and this chart details the 6 critical steps of the quantitative design review. This is an essential first phase of any fire engineering analysis. So the step 5 you can see here is very crucial because we define the specific acceptance criteria and how we will judge the design's success. So this structured process ensures a comprehensive and justified review before any complex modeling begins. So for the component of step 5, we identification the acceptance criteria. The acceptance criteria can be in several ways, such as the deterministic, because we can use some threshold like the temperature limitations. And they can also be probabilistic because they can base on some risk level. And we can also use the comparative criteria showing the equivalence to a prescriptive solutions. And after the component of step 5, we can take a look at this component of step 6. So this component of step 6, it is a story of a potential fire. That means we will establish fire scenario for our analysis. So the most important part of this scenario is the design fire. What does it mean? The design fire is our worst case scenario for modeling. Let's say we are analyzing the library. We don't just say a fire start. We should define it precisely. So our design fire could be what kind of list? A stack of newspaper ignites, and we focus on its heat release rate because the heat release rate grows very quickly and doubling every minute. And then the high smoke production rate fills the ceiling with the thick black smoke, and it releases a dangerous amount of the carbon monoxide. So then after that, we can track the fire size. That means the flame size and the time to the key events. So do you know what kind of the time to key events we should pay attention to? Such as the flashover. So sometimes the flashover occurs in 8 minutes, and this the whole story, the specific quantified story is our design fire. So it is a benchmark we used to test if the building smoke detectors and the sprinklers will work in time. So after the QDR, we move into the QA, that is the quantitative analysis. So to make this complex task manageable, BS7974 break it down into 6 subsystems. So we can use these subsystems individually to solve a specific problem, or we can combine them together to analyze the entire fire safety strategy of a building. So here are the 6 subsystems. So for the subsystem 1, SS1, it's about modeling how a fire starts and grows inside a room. So let's consider a real-world scenario to understand the output of the subsystem 1. So imagine you have a fire starting in a hotel room. So the fire is ignited by an electrical fault in a curtain. So by using the methodologies in PD 79741, we wouldn't say there is a fire. We would quantify it. So our analysis would calculate a specific heat release rate, perhaps showing it follows a very fast T-square growth curve and reaching 2 megawatt within 3 minutes. And from this, we can then determine the mass production rate of the smoke, like the carbon monoxide, predicting how quickly the room fills with the obscuring and the toxic gases. So this one is very crucial for our life safety. And then we can also predict the flame size and the temperature, and the rising temperature within the enclosed room, and the most importantly, the time to flash over. So what does it mean, the time to flash over? It is the time point that the entire room erupts in flames. So this specific time, we let's say calculated to be 8 minutes, becomes a vital benchmark for judging if the occupants can escape or if the sprinkler will activate in time. So the design fire, as we mentioned, is the cornerstone for the analysis. It must be appropriate to the objectives. For example, if we are designing a smoke extraction system, we need a design fire that will produce enough smoke to challenge that system. So it is kind of severe and the hypothetic fire. But please remember that a design fire is a conservation model. It is unlikely to occur in many practice. The real fire are often less severe, so the design fire is a tool for testing our safety system and to test their limitations to ensure the robustness. Okay, so having modeling the fire's development and its key output in the subsystem 1, we now turn our attention to the movement of its most dangerous byproducts. So the subsystem 2 focuses on the spread of the smoke and the toxic gases, both within the room of origin and to the adjacent space. So analysis in subsystem 2 range from some simple equations, such as for the smoke filling the room, to some complex computational fluid dynamics model that will simulate smoke movement through the whole buildings. So the choice of whether simply equation or some CFD models will depend on the complexity of your problem. So you can have more details from the figure 5 in BS 79742. And then we will discuss the subsystem 3, that is for the structural response and the fire spread beyond the enclosure of the origin. So let's make it practical. You can imagine a fire in a modern office building that is an open plan floor. Firstly, we must evaluate the fire severity. So the fire severity, we can use model from PD 79741. We can calculate the temperature and the heat flux from a growing fire. For instance, we might determine that the fire will cause temperature at the ceiling to exceed 1,000 degrees centigrade. And then the second step, we assess the structural response. So let's consider a steel beam that's supporting a floor above. So can they withstand this very high temperature exposure? Nearly 1,000 degrees centigrade temperature exposure. So we might find that if the steel beam is unprotected, this beam would lose their strength and it will show a very excessively deflection after only 15 minutes. So this is a very risky phenomenon because it will lead to some collapse and allowing fire to spread vertically. So this quantitative analysis of both the fire's severity and the structural ability to resist it in the core of the subsystem 3, ensuring our design for safety and the stability. So as we know that the fire can spread through various mechanisms. It can spread by conduction through a steel beam and by convection through an open door or a ventilation duct, and also by the radiation through a window igniting another building, or even by direct flame. So from this example, we know that the methodology for subsystem 3 firstly involves defining the fire enclosure. And the analysis then evaluate the element's thermal and the mechanical performance under this environment. And after defining the comparing with the critical failure criteria, we can predict the failure time and the duration before the fire spread beyond the whole compartments. So after analyzing the structural response and the potential for fire spread in subsystem 3, we move on to the subsystem 4. So the subsystem 4 is fundamentally above time. So for the subsystem 4, it will provide the methodology for calculating the essential time. This kind of time interval will from ignition to the delay until the detection, and the subsequent activation of the alarm and the protection system, like the sprinklers or smoke vents, will finally be alerted of the fire service. So after that, in subsystem 5, we should evaluate the capability of the fire service. And based on the information that the previous subsystem provided, we finally come to the most important subsystem, that is for the evacuation. So the subsystem 6 provides the guidance on how to assess people response to a fire and how to estimate their total evacuation time. So it is important to know that the criteria for acceptance is contained in the subsystems. And all these subsystems would give us a clear guidance from the fire ignition to the evacuation. So it will construct our whole quantitative analysis. So now we come to a fundamental concept that brings all these subsystems together. What does it mean? The timeline approach. So the timeline approach is the core of performance-based design. And it is very important for us because it can get all the subsystems together. And the principle of the timeline approach is very simple but very powerful. So you should take a look at this slide. For the life safety to be achieved, the available safe egress time, that is ASET, must be greater than the required safe egress time, that is RSET. So ASET is the time from ignition until the condition in escape routes become untenable. So we define the untenable conditions based on some criteria like the smoke layer height, the temperature, or the visibilities. So this available safe egress time can be estimated from different modes. And this diagram visualizes the race between the fire and the people. So it starts at ignition. So we can put this red line as the ignition time. So after a short time, the fire is detected and the alarm sounds and the people start to react. So the pre-movement time is the delay before people start moving. So we can have the detection time and the pre-movement time. Then the traveling time begins. That is what the time people need from their reaction to their get exit. So the summation of the detection time, the pre-movement time, and the traveling time is the RSET, the required safety egress time. Meanwhile, the fire is growing, and the fire growing reduces the ASET, that is the available safe egress time. So the safety requires that the evacuation is complete before the conditions become deadly. Okay, let's take an example. Let's imagine a fire in a student dormitory. So at the ignition, a very small trash can make fire start, and it takes only 30 seconds for the detection system to sense it, and it takes another 30 seconds for the alarm to sound. Then the clock starts for people. So the pre-movement time is crucial. The student might take a minute to recognize. They may take a minute to recognize the alarm and grab their phone and check the whole way. So that is the delay before they even start moving. And then the traveling time begins. So how long it actually takes them to walk to the exit and reach safe. This total time is the traveling time. And the available safe egress time is the total time from ignition until the whole way becomes filled with dead smoke. And the required safe egress time is the total time people need to detect, recognize, and escape. So you should just remember the golden rules of the fire safety. That is, ASET must be greater than RSET. So this is the RSET equation. And as we mentioned before, the RSET is the detection time plus alarm time plus pre-movement time plus travel time. So the detection time can be estimated from some empirical models. And the alarm time is usually very short. Then the travel time can be simulated with some software like Simulex or Steps. So the most variable and uncertain factor is often the pre-movement time. So why is the pre-movement time so uncertain? That is because the human behavior is complex. People's reactions are affected by their state, such as they are asleep, they are awake, they are dresses or they are undresses. And also, they are relying on the building design and the fire protection device. So many people will not evacuate immediately. They may seek for some information, gather the belongings, or even help others first. So estimating the pre-movement time requires understand the cognitive ability of the occupants. So will they recognize the alarm? So will they wait for confirmation? And this value is highly uncertain and is often a major point of discussion and sometimes disagreement between the designer and the approving authorities. So we need to get accurate data on occupant profile. And similarly, the estimating traveling time depends on physical conditions. The physical conditions, such as occupant distribution, occupant density, and the age, and the mobility, and the gender. So this is no universal guidance for selecting this input parameter, which again can lead to some debate. So this is another reason why we need performance-based design. So based on the performance-based design, both the pre-movement time and the travel time can be simulated in our software. Sometimes we can get some input data such as the occupant density, the building design, the building layout, and the fire device to get the total such as the ASET. And then we can also get some simulations from our software to get the total RSET. And that is easy for us to compare both of them and to see whether it is for our, such as the golden rules, that ASET is greater than the RSET. Okay, so after that, we understand the ASET and the RSET. That is for our quantitative analysis. And based on the quantitative design review and also the quantitative analysis, it is the basic outline for the BS 7974. And you should take this part in some very critical part for your design. And we maybe have some questions in this part in our final example. Okay, so let's take some rest for 10 minutes, and after that, we will move on some other part for the application of the fire safety provisions. So have you submitted your report of the assignment 1 to the Blackboard? Okay, so tonight is the deadline. Okay, so let's start. And in this class, let's move from the theory and analysis to some practical hardware. So that is the application of active fire safety provisions. So anybody knows some fire safety provisions? Can you give some examples of this equipment, both for detection or extinguishing? Is any volunteers to answer the question? Anybody knows? No volunteer. So I will ask some students to answer the questions. You can just give 3 examples of the equipment. Okay, this one. You please. Just give an example of the equipment you know about the fire safety provisions. Yes, that's great. And any other things, equipments you know? You can take a look at around the classroom. Yes, that's great. Okay, so I will mark your name and you will get higher grade in the final exam. Okay, so today the application of the active fire safety provisions, we firstly need to know this kind of system. So the system requires some triggered action to work, both automatically and manually. And this is for our fire detections. The choice of the detection depends on the fire scenarios. So a fire in a large atrium will behave like a free burning fire. And where some fires in a confined room, that is as our classroom, may produce some toxic gases and creating a potential severe hazard. So our fire signatures of heat, smoke, light, gases will decide the type and the location of the detector. So do you know what is this one? The smoke detector. I think you have ever seen this kind of smoke detector in your dormitory or in your apartment, right? So the smoke detector, we have always distinguished them into 2 main types of the smoke detector. The first one is ionization smoke detector, that is a very fast response to flaming fire or high energy fire. And it can detect some invisible and visible small smoke particles. And the other one is the optical smoke detector. So the optical smoke detector are better at detecting the large visible smoke particles from the smoldering fire. So always we use the combination of these 2 kind of smoke detector to get a better coverage. And here, as we know, many fire will produce some characteristic gases, and the carbon monoxide is always present, and it's a very good early indicator for fire. However, the amount of the carbon monoxide produced depends heavily on the fuel and the ventilation conditions. So it increases rapidly in under-ventilated and oxygen-starved fire. So that is why we need carbon monoxide detector for the early warning of this kind of fire. And after the detection, what we need to do is to extinguish the fire. And as we all know, water is the most useful way, but sometimes we don't use water. And when do we avoid water and use gas instead? We use gas in place of water. In some place that the water would cause more damage than the fire itself, or where it just won't work. So the classical example is the room filled with sensitive electrons, or the severe room, or some tactical switch room. So in this kind of room, the water would destroy the expensive equipment and will cause a massive business disruption. And similarly, in the place like National Museum, some precise items in the National Museum, the water would destroy the very things we are trying to protect. So instead, the gas systems are also very crucial for the three-dimensional hazards where the water cannot easily reach, like in the engine bay of the ship or in a large industry printers. So they work by flooding the space with chemical gases, rapidly reducing the oxygen level and snuffing out the fire without leaving any residues. So this is a kind of gas protection system, and we can see it in most of the building of our university. So here we need to mention that some total flooding. Total flooding is that we fill up the related compartments or areas with adequate gas to achieve the minimum to concentrate for effective firefighting. In this behavior we call total flooding. And the total flooding is another one we pay attention to. The total flooding, a typical total flooding system has several key components. We have the gas cylinder, and we have the trigger mechanism, such as the detector or manual core point. And we have a network of pipes, and we have the discharge nozzles that are placed to ensure even the distribution of the gas. So there are also some safety devices to prevent the accidental discharge. And from this figure, we can see the total flooding system are composed with this kind of components in their systems. And when we design the activation system, we need them to be smart. We want the system to be reliable enough to activate when we need it, but we need them to be also safe enough to avoid accidental discharge. So that is why we use strategies like the time delay for evacuation, and we use some cross zoning to conforming a real fire, and the manual overrides for firefighters. So that is means we need to firstly conform the fire location, the fire flame size, and even the temperature. And we need then to activate immediately after we conform the fire. So that is our activation strategy. So now let's look at this one, the sprinkler system. We always think that the sprinklers not as one single system. The sprinkler system is always different tools for different jobs. We have some web pipe system. This one is like our everyday workhorse and always ready with water. But in some freezing conditions, such in the North Europe, we use a dry pipe system to prevent the frozen pipes. And also for some high hazard area, we have the deluge system that will behave like a heavy rain. And we also have the foam fire system and the precaution system. And all of these will construct our sprinkler system. So the sprinkler system includes a very important water supply in some tanks or in some pumps, and include a network of pipes throughout the building, always up to our ceilings or in our walls. And also we have the sprinkling head. So in the left figure, we can see this kind of sprinkler head. This is a typical sprinkler head, and the key component of the sprinkler head is the heat sensitive element. That is a kind of temperature dependent element, and it will react or it will activate if the temperature reach to the criteria. So after our sprinkler system, we have this one, hose reel. I think you may have likely seen this kind of hose reel in the building corridors, such as in the MTR or in our universities buildings. And the hose reel are provided for building occupants. You should remember it is provided for the building occupants or initial firefighting by staff. So they are permanently connected to a water supply and have a simple nozzles. You can see here it is a kind of pipe that connected to the water supply, and it required the fire safety instrument that allows the firefighters to fight fire. And by using our code of practice, they can find the requirement on the hose reel of their tubing length, their flow rate, and the water supplement applications. And here we have this one. It is a kind of fire hydrant. So what is the fire hydrant? It is another required fire safety instrument. The fire hydrants are used by the trained fire service, so they are outlets in stairwells or lobbies. The firefighters are able to connect their hose to the fire hydrant. They are part of a dedicated riser system with a much higher water pressure and the flow capacity than hose reel. So always the hose reel and the fire hydrant system are integrated into a single system. And they always share the same water tank, water pumps, to get the water supply and the main piping network within the building. Okay, so after this kind of fire hydrant and hose reel system, we take a look at this trencher system. So the trencher system, despite the fire inside the building, we should also look at the fire outside the building. So this image illustrates this kind of problem. The fire can spread out through the openings, exposing other part of the building or adjacent building from the radiant heat. So that is why we need the handrail system to help mitigate this kind of risk. Okay, the trencher system are like sprinklers for the outside of a building. They are used to protect the building's exterior from an exposure fire. And they are typically installed on roofs and above external window. But the trencher system can also be used internally to create a water curtain. The water curtain helps us to block the heat radiation and may also help to wash the smoke particles out of the air. And this is a kind of typical pattern of spray from the drencher head. This kind of typical pattern of the spray usually installed in every corner of the the drencher system to ensure that the complete coverage of the protected area without gases. And it is important to understand that a drencher system is primarily for exposure protection. So the exposure protection, it is not typically designed to control or extinguish the main internal fire itself. So the drencher system, its job is to absorb radiant heat and protect adjacent area. And this diagram illustrates this kind of principles. By using the drencher between these two kind of compartments, the fire zone will be significantly extinguished, and the water curtains will absorb the heat radiation. For example, in Hong Kong's high-rise building, the refuge floors are a very critical safety requirement. They are fire-protected floor space throughout the building, where the occupants can get rest safely during a stage evacuation. So the drencher systems must cover all external walls to protect against the fire spread, and that is its important function in Hong Kong tall buildings. Okay, now we take some work example. Let's move from the hardware to the software. To perform the quantitative analysis we discussed earlier, we use some engineering tools. So the fire dynamic simulator, which is in short FDS, is a leading computational fluid dynamic model developed by NIST for simulating our fire-driven fluid flow. And we can also use the smoke view, SMV, to visualize our fire simulation results, such as the smoke movement, the temperature profile, and also some other impact. So these are the tools we use to calculate ASET and RSET and to model the fire and the smoke spread. Okay, here is a very short video for using the FDS. Firstly, we import the CAD model. It is a kind of building models. And after that, after we import the building models, we can zoom it in and also zoom it out. And then we specify the fire. We can specify the heat release rate and also some flame size. And then we place them directly into the 3D model. This is a 3D CAD model and generate our final results. Okay, here we run our parallel FDS simulations, and we can see the results in the smoke view. So that is the smoke view. We can input our simulation data into the smoke view software, and we can see the smoke movement during the fire compartment. So here, let's move to our case. What is our case? Our case study is a very interesting topic. It is a 6-story office building with a basement. So the basement, we name it the floor 0. And the clients want to change the use of the floor 0 to floor 3 into a nightclub. And the floor 4 to floor 6 will remain as office. It is very interesting, right? Transform the office building into a nightclub. So this change of use triggers what? Triggers a kind of re-evaluation of the entire fire safety design. And as we have seen in the FDS simulation, we firstly input the building size, the building model. So this is our building model. And the floor area is almost equals to 370 square meters with the height of nearly 20 meters and the height and for the floor, let's say 1, 2, 3, 4, 5, and from floor 1 to the floor 6 it is nearly the height of the 18 meters. So the floor area of the upper floor, like 1, 2, 3, 4, like the floor 4 to the floor 6, is smaller than the basement. It is only nearly 230 square meter. So we mentioned that the varying size, the varying floor area will influence the occupant load and the evacuation dynamic. Let's say for the large floor area, we can have more people. That means the more occupant density. And if this more more people want to evaluate from the floor, we need to design a more effective evacuation dynamics. So the initial check will be happen for floor 4 to the floor 6. So the initial check show that the upper office floor still comply with the codes, comply with the code of escape and the code of access, which is for our building design. Because the building structure is strong enough for new installations and they meet the fire resistance requirements. And the staircases comply with MOE code, and the lift capacity is sufficient. So the problem will lies in other place. Okay, so from our occupant load from the MOE code, the means of escape code, we can calculate the total occupant of each floor and get the summation of the whole nightclub occupant. So as we can see here, for the floor 0, the storage area 1, and we have the kitchen, the dining area, and if we don't have the dance hall, we can get the occupants of 147. And for the floor 1, we have the kitchen, we have the dining area, and here we also have the dance halls. So the occupant will rise to 194. And for the floor 2, we also have the kitchen, dining area, dance hall, and it is 117 people. And for the floor 3, we just have the kitchen and the dining area, and it is only 21 person. So also it is only 48%, and also we consider about floor 4 to the floor 6. It is a kind of office floor. So each of the floor we have 21%, and the totally the person reaches the number of the person reaches to 569. So it is a very large number compared to the previous buildings. So the number increased significantly to 569 people compared to the original office used, and this immediately stress up the escape routes because more people need to escape from our escape routes. Okay, so also we need to the further analysis reveals that the specific non-compliance with the means of access code. What does it mean? Firstly, the lift area is too small for a fireman. The lift area is only 2.21 square meter. It is very small for the fireman to evacuate this kind of number of people. And also, we don't have enough smoke separation between the lift lobby and the staircase lobby. That is the major issue because the smoke could enter the escape stair and it will enhance our visibility and infect our evacuation effect. And also, the smaller corridors width will it is under the requirement of 1.5 meter and will lift to the fire and this will lead to a fireman's lift. And this seem very small but are critical for firefighters' access. So this kind of non-compliance to the means of access code will require us to upgrade our evacuation method. So what will be considered in our fire service installation design? This is another code we need to be met. So due to the change of the use and the increased hazard, the fire service installation must be significantly upgraded. And let's see what's required. There is a very long list of the fire service installation required for this categories, such as the audio or the visual advisor systems and the emergency generators, emergency lightings, exit sign, and the fire detection systems. This is a very, very long list for our fire service installation requirement. And because this is a commercial building with a basement over 230 square meter, the fire service installation codes requires this very long system, and most of them should be needed. But the biggest change is to the sprinkler system. The fire hazard classification changes from the ordinary hazard 1 to the ordinary hazard 4. This is a very significant change and required a much higher water density and flow. And consequently, our water storage tank size should be also upgraded from just 55 cubic meter to 135 cubic meter. It is more than double. So the new pumps and the valves are also needed for our upgrade the sprinkler system. Okay, so that is our fire dynamics simulator building layout. Regarding this necessity, let's look at what the fire dynamic simulation tells us. And this is a 3D model for the building created in the fire dynamic simulators and visualized in smoke view. So here it includes the geometry, the walls, the doors, and the windows, which are all essential input for the simulation. And in the simulation model, we define the boundary of the building and also the internal partitions and the walls, and also some openings like the windows and the doors. So anybody knows why this kind of boundary of the building is very important? Is any volunteers to answer the question why this kind of boundary of building is very important for our design? Okay, because the boundary of the building means the evacuation of our people. Sometimes it means the smoke movement and sometimes it means the visibility, and sometimes it means the heat radiation change. With this kind of boundary of the building, the visibility, or in other words, the smoke particles can be released from our building. And also, the heat radiation can also be released from our internal building to the outside, and our smoke particles, our visibilities will be improved. So the boundary of the building is very important as an input factor for our fire dynamic simulation. And in our fire dynamic simulation, we should not just simulate one fire. We should simulate multiple fire scenarios in different location and with different heat release rate to find the worst case. And here we can see we have the 8 potential fire locations. These 8 potential fire locations were identified on floor 1 to floor 3, and the design fire is of 2 megawatt. The 2 megawatt design fire was used for this simulation. And we can take a look at this kind of figure. The case 1 in the corner, and in case 2 is in the center of the nightclub, and in the case 3, case 4 is the fire scenario is behind the window of our compartment, and the worst case will be the case 5 and the case 6 because there are too many people in the compartment. And we also have the case 8 and the case 7 on the different corner of our compartment. Okay, so this is what the fire dynamic simulator tells us. And let's take a break of 10 minutes, and we will look at the smoke video of the worst case, case 5 and case 6. Okay, take a break. Wait, what? Okay, sure, sure, sure.
誒，喂，我想問一問有冇以下名嘅同學仔喺度？因為我哋俾人編嘅同一 group 嘅。林希銘，如果有可以認一認我，有冇？林志雄有冇？冇。陳明軒有冇？都冇。伍迪豪喺咪度？都冇。好。
You can send their email. So
I send.
you already sent.
Okay.
So they don't reply.
Yeah.
Okay, I will let them know. Okay, let's continue our class. So, as we mentioned before, we are looking at a 6-story floor that they want to transform the floor 0 to floor 3 into a nightclub. And we mentioned their building layout and the simulation of the smoke spreading by using not only one fire scenario, but we use 8 fire scenarios. So there is our 8 cases, different file scenario, and we estimated the file size. They are all of the file size are equals to 2 megawatt in 1 square meter. So I want to know which case or cases you think is the most severe case in this kind of smoke spreading simulation. We have case 1 in the corner. We have case 1 here in the corner of the toilet, and the case 2 in the kitchen, and the case 3 might be a dance hall, and the case 4 might be the bar, the night bar, and the case 5. That is a kind of very large compartment. Case 6, a kind of dance hall as well, and the case 7 and the case 8 both in the corner of the floor. So which case do you think is the most severe condition for the people in these floors? Is any volunteer to answer the question? Which case or which cases do you think is the most worst case for our simulation? Any volunteer? If you answer the question, you might get higher grade in your final examination. Okay, so I will ask students to answer randomly. Which case, or which cases you think it is the most worst condition for the occupant? Okay. And any volunteer? If not, I will ask some student to answer. And this way. Just feel free. It's important to answer the question. It is not about correct or not. Just answer it. It's a good practice for you to thinking of and understand our simulation.
It's 5 of 2.
Let other students know your opinion.
In case that there is no huge fire in the middle of the grass, maybe case 5 because
Case 5. You think it's case 5, right? Case 5. So why you think it's case 5?
and I think the occupant load for the case 5 for the dance floor will be very high. So
That's very great. So case 5 is actually the worst case condition in our simulation. That's a good answer. And your reason is also very convincible because you think it is a kind of dance hall, right? It's a dance hall and it will have several or too many occupants that join in the dance and appear in the dance hall, right? So that's right. It is the one of the worst cases in our simulation. And also, in the same floor, case 6 is also the worst cases. And you can have the same reason to consider it as the severe condition for our simulation. Okay, so okay, what's this? So by using our fire dynamic simulation, we can get the snapshot for smoke video of the case 5 and the case 6 in the floor 1. And as you can see here, the case 5 and the case 6, we will get the movement of the smoke. The visualizing the smoke flow is powerful for understand how quickly the escape routes become blocked. So what's the condition of this kind of escape routes become blocked? Anybody knows? So what's the condition of this kind of escape routes becomes blocked? Sometimes we can use the smoke concentration, and sometimes we can use the visibility of the occupants. So if we have no visibility in our escape routes, it will be blocked. And if the smoke particles, the concentration of the smoke particles is very, very high, it is also deadly dangerous for the occupants. So that is why we need the simulation of the smoke movement from our fire dynamic simulation. So the worst case in this study at flow 1, this is the simulation output for the, and let's say for the visibility. So we can see that the temperature and the visibility in both 75 seconds and the 77 seconds, it is only 2 seconds difference. But for the case 5, in both case 5 and the case 6, the temperature and the visibility have significantly changed in this very short time interval. So we can see that the temperature exceeds 200 degrees centigrade and the visibility drops to 0 in the large area. So what does it mean? It will give us a very, very short ASET, that is the available safe egress time. So the temperature rises, the visibility down, and also some smoke particles will spread over the whole compartment, will shorten our ASET. So that is why we need the simulation to get this very important factor of our ASET. And this is our escape routes. The escape routes for floor 0, floor 1, floor 2, and floor 3 are shown here. But we should note that the main exit is in floor 1, and the main exit is here. So the main exit location is very critical for us to ensure the occupant safety in the whole buildings. And we can see that the escape routes for the basement, that is the floor 0, is a very, very simple way. And also for the floor 1. So that means many occupants will be crowded in the main exit of the floor 1. So by using our simulation, we can check if this route remains usable long enough for everyone to escape. So if the route remains usable, that means we have enough time to escape. But if it is not usable, or not usable long enough for everyone, we should upgrade the escape routes. Okay, and this is another figure, and it is a very important figure you should be noted. And this graph shows a simulation where the sprinkler system operates. So as we can see here, the heat release rate increase significantly with the time, and with the time at almost the 200 seconds, the heat release rate reaches to almost 2,500 kilowatt. But if we use the sprinkler control, then what happened? If we use the sprinkler control, we can see that the heat release rate becomes stable. So this figure demonstrates that how vital a properly designed the sprinkler system is while extending our available safe egress time. So you should keep this figure in mind, and it is a very good illustration to see how a good sprinkler system should work. It will stable our heat release rate in after a second or some hundreds of seconds. So this is our sprinkler control. And after that, let's see, we have another very important profile, that is the temperature profile at floor 1. So what does this temperature profile means? You can see several lines in the figure. And what does it mean? It is a kind of temperature versus height at different time, from 100 second to 600 second. So this chart shows us the heat from a fire builds up over time, layer by layer. So in the time of 100 second, it is this blue line. So the temperature is nearly 20 degrees centigrade at all height of our building. But this is just the start of the hot smoke layer forming at the ceiling. Now we watch what happened over time. So each new line, the red one, the green line, the purple line, and the orange line, it shows the temperature difference with the height, with the time variations. So the heat shows the bunching down towards the floor. And by this one, by the orange line, it is a kind of 600 second. This line shows that the temperature are getting dangerously hot, even at the head height. So this is a very crucial point for us. When this hot layer descends to where people are trying to escape, that means if our people trying to escape from an escape route, but the temperature of all of the height will be very, very, very high, we cannot get the escape from this route, right? So this is a very crucial time point. And when this hot layer descends to where people are trying to escape, it will create severe conditions. So this graph gives us the exact timeline of that hazard and showing us how long people have before the heat itself becomes a deadly barrier. So if we set that the temperature should lower at the 55 degrees centigrade and under the 2-meter height. So what will be our escape time? What will be our escape time? Our condition is set as we need the temperature under 55 degrees centigrade, and the height of the temperature should be lower at 2-meter height. So we can say that this point should be our critical time, right? So it is about 200 seconds. So it is only 200 seconds for us to escape. And also we can see here another very important figure from the fire dynamic simulator. It is about the visibility profile. So this figure tells us a very simple but a very scary story about how quickly smoke fills a space. So each line shows visibility at different time. So look at the blue line at 100 seconds. You can still see about around, let's say, 15 meters ahead near the floor. Because the height, we only we consider about the height under 1 meter or under 2 meters. So this part of the figure is very important. And for this line, the blue line is around 100 second. 100 second, we can see that the 15 meter ahead near the floor is still available. But just 200 seconds later, at the 600 second market, the story changes completely. The orange line, this one, the orange line shows the visibility has crashed to almost zero at all heights. What does it mean? It means that we are now in a very black box. We have no visual visibility for our escape routes and also for our compartment. So that is why we talk about a golden hour to escape in fire. It shows us that we don't have 10 minutes. We often have just 2 to 3 minutes before our escape routes become impossible to see. So let's also consider a very important time, such as this one. If we want to have a visibility of 10 meter at or below the 2 meter height, so this time point will be our critical time. That is 200 seconds. So it is just nearly 2 minutes to 3 minutes for us to escape. Okay, so this kind of profile, temperature profile, smoke profile, and visibility profile are all from our fire dynamic simulation. And it is a very important critical time and also very important simulation for the escape routes for our designer. So besides the available egress time, we also need to calculate what the required egress time. So what we mentioned before is about the available egress time, but we need to calculate the actually required egress time. So we need another model, that is evacuation model. So this evacuation model requires a detailed layout and an accurate estimation of the number of people. So we need to understand that the most important part is the number of the people. So here we estimate 174 people on the nightclub floor at the time of the fire. So we have 90 people in the floor 1 and another 85 people on the floor 0. So the total number will be 175 people. So this is the layout plan for our evacuation study. So here we need to understand what will happen after 100 seconds and 200 seconds. So the total number of the occupants, as we said before, is 175 people. So from the evacuation simulation, we can also conduct the evacuation simulation from our fire dynamic simulator. The video will show us that the movement of people at 100 seconds and 200 seconds. So here is a flow chart for the number of people, for the change of the number of people with the time. So with 175 people, the total evacuation time, which one do you think should be the total evacuation time? We have the purple line and we have the red line. The purple line means that all of the people have been evacuated from the flow 1. And the red line shows us that all of the people have been evacuated from flow 0. So the total second or total time we need is around 100 second and nearly less than 150 seconds. So this total evacuation time will be our required safe egress time. So remember, do you remember our golden rules? What's this? What does it mean? Our golden rules. That means our available safe egress time from the fire simulation should be greater than the required safe egress time. But here in our simulation, the fire dynamic simulator tells us that our available safe egress time is about 75 to 80 seconds in the worst case without sprinkler. So here we have a problem about the required safe egress time is greater than the available safe egress time. So that will means unsafe. This is an unsafe plan for our people evacuation. So how can we fix this problem? So anybody knows how can we fix this problem? By your own opinion, you can just propose some of the idea to fix this kind of problem. So any volunteer to propose some idea for us to fix that problem? We already know that our required egress time is greater than our available egress time. So what do you think we can do to fix that problem? You just need to propose one idea. One idea is enough. You can also ask ChatGPT or DeepSeek to answer this question, but you should just join our class and think of it. Any volunteer for our question? Okay, so let's ask a student randomly. Maybe, okay, you're a volunteer. Great. Add more exit. Okay, that's a good answer. And the staircases, that's great. And any other idea? Okay, your answer is very good. So that is what we will do for our designer in case this kind of situation. The most important way is to adding more exit, and the other things will be we can limit the number of people showing in our compartment or showing our nightclub. So firstly, we can limit the number of people in the nightclub to reduce the evacuation time. Then, as the student said, we can create safe zones by adding the smoke lobby and the self-closing doors to protect the staircases from smoke. And alternatively, we can also add more staircases as well. And finally, we can install a dedicated smoke control system to push the smoke away and give people more clear air time. So we can see that we have two key ways. The first one is that we can add more evacuation time, that is, extend our available evacuation time, or we can shorten our required egress time. So that is the key way for us to tackle this problem. And by using this way, we can both shorten the escape time and also extending the safe time by using this kind of solution. Okay, so what this work example tells us? Firstly, if we just follow the rule books, it's not always enough for this kind of complex building, because you may also meet some other complex building, such as a combination of the nightclub with the office building, or some other design, such as a very large atrium or a very large open plan floor, and only following the rule books is not enough. And secondly, we can upgrading the system. Upgrading the system, like such as add more exits, or add more some sprinkler systems, add more some smoke control, can significantly extend how people have extend the time of people have to escape from the compartment. And finally, we should have a clear fire safety plan and the good management. This is very crucial to make sure that everyone reacts quickly in an emergency. So that's our conclusion for this worked example. And which one do you think is the best one? In these three rules, which one do you think is the best? They are equivalently important for us in both shorten the evacuation time and the required evacuation time, and extend the available egress time. Okay, so let's see that some evacuation model. Here is a kind of evacuation model. What does happen? So in some evacuation model, they are very simplistic. They are very simplistic to treating the people like a robot, just moving in some optimal path. So more advanced models incorporate the complex behavior, but the input data is still challenged to obtain. That means we cannot treat people as robots. People cannot get evacuation in some certain paths. They may get some other behavior, like grab the phone, like help others, or they should also get dressed first. So we cannot only treat people like robots. So the input data is still challenging to obtain. So we must be not over rely on the apparent accuracy of this simulation. That means in the fire dynamic simulation, sometimes the simulator treat people as robots, and the design they give us will not be sufficient for our real scenarios. So we must not over rely on the simulator. We have to be careful with this kind of fire engineering approach. It is truly a very powerful tool, but can be misused. Some designer might be tempted to use unrealistic small file scenario to make their number look good, make their data look good. Or they might assume everyone evacuates like a robot, ignoring how people actually behave in emergency conditions. So we have also mentioned in our BS 7974 that people sometimes have multi-behavior, and we need to know the accurate occupant density, the gender, and their ability for their evacuate. So that is what we all need for our design. And also, the fire engineering approach design can create buildings that the firefighter are not very familiar with. That means they will have some innovative buildings with large open plan, or they will put some sprinkler systems in some other corridors. So our firefighters will not be very familiar with this kind of buildings. Their training is often always based on prescriptive code buildings. And if the fire engineering approach design has some unusual layouts or smoke movements or the system operations, it may pose the challenge for our firefighting and also put challenge for our rescue unless they are specially trained for it. So it has been demonstrated that such training would be appropriate for fighting against the fire in a building that are equipped with fire safety provisions stated in the prescriptive code, right? But is there any training for the firefighters for the equipment of the fire safety provisions for our fire engineering approach? I think there are few trainings for our firefighters. So this is another concern for our using performance-based design. Okay, despite this concern, it's very important to state that our fire engineering approach is a good and a necessary practice. So it allows for innovation and solve the problems where the prescriptive codes are too restrictive. And it also aligns with the international standard that the best practice in the performance-based design. So the fire engineering gives us a smarter way to design safer and more innovative buildings. So this is the takeaway of our class. So you can take a picture for this slide. But our fire engineering approach is not about finding shortcuts. It demands our careful choices about the fire scenario, honest data about how people really behave and the realistic building conditions. And most importantly, we must always remember that behind every calculation, there are real people whose lives depends on your professional design. So this is your duty, and you should be very careful when you use whether prescriptive code or fire engineering approach. Okay, so do you think there is some realistic example for our prescriptive approach? I think I can propose one. You know that the Henderson building in Central, the new building, it is based on our fire engineering design or performance-based design because its exterior appearance is not like our traditional or conventional residential buildings. It uses the glass wall, which have the different fire thermal resistance, and will have the different axes in the whole buildings. So this is an example for our fire engineering approach design. And can you please also propose some other examples for this kind of buildings? You can also use ChatGPT or DeepSeek to seek for the answer. Because in Hong Kong, it is a very highly density urban and also some other cities like Tokyo or Shanghai. So we can meet several buildings with some innovative appearance or some innovative internal design. So we can know that this kind of building, some of them are with the prescriptive code, but some others are from the fire engineering approach. So you should know some of these buildings and get better understanding of our fire engineering design approach and its usage in our real world application. So do you have get answer from ChatGPT, right? Any volunteers to answer our question to give an example for our real world application of the fire engineering approach? Any volunteer? And I mention again, if you be a volunteer, you will get higher grade in your final examination. Or I will ask some students to share their opinion on our building examples. Okay, I think you have get enough time. So okay, so could you please give us an example on our fire engineering design approach? Just share your opinion, and you don't need to care whether it's correct or not.
Sorry, we can follow the correct
Metro railway.
yeah.
Okay.
We can leave in the correct way.
Okay, that's great. That's a very interesting answer. He said that some system, right? Some sprinkler system or some other systems in our metro railway, in our railway station, may use the fire engineering approach because the station would have some different appearance or internal design. That is very interesting answer. And anybody want to share your opinion for our example? Okay, great. I think it can be a homework for you to think of the real world application of our performance based design. And that is our some reference for your takeaway. In this list of the key reference, we have the fire dynamic simulation and the smoke reel guidance and the Hong Kong code of the practice and some essential textbook and the lecture notes. So this brings us to the end of this lecture. In the rest of the time, I want you have some knowledge on your assignment too. So you can open your sign in your Blackboard. I have assigned our assignment 2. I have assigned our assignment 2 today, and have you ever seen it? Okay, so for our assignment 2, it is a seminar group project. And I think you have already formed your group before this class. And you can choose one of one of the topic from these 4 topics. The first one is legislative challenge and the solutions for maintaining fire safety in heritage buildings in Hong Kong. And in this topic, you can discuss the legislation on building control and consider how to balance preservation with modern fire safety standard in deal with adaptive reuse of heritage building. And you also need to give a case study of successful fire safety upgrades in the kind of heritage building. A case study should be in detail, not just say their names or their place, but in detail, please. And the second topic is addressing the unique challenge and the legislative requirements for fire safety in super tall buildings. And you should state the specific challenge for these super tall buildings, such as the evacuation and the fire spread. And you can discuss some strategies and the use of advanced fire safety system like pressurized stairwells and the refuge floors. A case study of the fire safety requirement is also a super tall buildings, as we have mentioned in this class, the refuge floor, right? And the third topic is to ensuring complying with fire safety regulations in building design for public assembly. You should notice that the keywords is the public assembly. So the fire safety regulations for public assembly building, such as the theaters or some classrooms. So the legislative requirement for coping with the large crowd, multiple exits, and the fire suppression systems and the emergency response or the regular fire drills should be noted in this topic. And the final one is the comparing the prescriptive codes with the performance-based fire codes and their impact on fire safety managed practice. That is what we have learned today. So you should state the difference between the prescriptive and the performance-based code in providing fire safety in buildings. And you should provide a case study to compare the effectiveness of both approach in a real-world scenarios, such as hotel. So that is why I asked you to share some realistic real-world application of the fire engineering approach design. So I think you may have 3 people to 5 people in your group, and each of your group will have 6 to 10 minutes presentation, followed by a 3 to 5 minutes question and answer sessions. That means each student should have 2 minutes presentation and 1 minute question and answering. So you should, each group member should present it evenly the time. So the presentation will be assessed according the following rules. And after your presentation, you should upload the presentation slide as well as your individual slide, as well as your individual reflection. The individual reflection will be what you learned from our courses, how you learn from our courses, both technically and personally. So you can propose some of your new ideas for our courses, or you can just state what kind of techniques you have used to learn our course. It's just a kind of individual sharing, so it should be submitted as well as your PowerPoint slide to after our presentation seminar. So the presentation seminar will be held on, I think it's 11 November. I think it's 11 November, right? No, it should be the 17th November, 10th and the 17th. It will be held on 10th and the 17th of the November. So you have enough time to prepare for your seminar, group seminar. And also, you should note that the generative AI is permissible, but you should also make the deadline of the use of the Gen AI tools in your work. You should fill this honor declaration of assessment. Okay, so that is all for our assignment 2. And any question on our assignment 2 on our seminar group? I think you have know which group you have been involved, right? Okay, and I also upload the schedule of our seminar. You can also find in your Blackboard. So this is for day 1, and we have 12 groups. And also day 2 means 17th November, we also have 12 groups. So if you cannot attend your group seminar, please send me or send Dr. Gigi of your business trip tickets to let us know that you are not able to attend the group seminar because of some business reason. Okay? Okay, so any questions on our assignment 2 seminar group project? And you should also submit your assignment A1 report from the Blackboard tonight. Okay, so is there any questions on our class today? No? Okay, that is all for our class today, and have a good night.